So, and again, you're all busy getting your feedback and doing your homeworks and doing your project reports, which is good. And speaking of which, if you remember, I told you early on in the semester when you did the projects that I had this thing like, okay, if you can actually take a paper and do something and improve it and get something submittable out of it, you'll get automatic A. So I've been saying this every year, and ever since I started teaching this class and doing this project thing. So it's been many years, and everyone just laughs at me, and like no one ever actually sort of comes through with that. So even I just like, I'll just tell you. So I would like to, and I'm very happy to announce that this year is the first time in I think 4 or 5 years that someone has actually, well, how should I say, won the prize for taking a paper for their project, actually improving it, generating a paper out of it that's submittable, that actually was submitted today morning at 5 o'clock for a conference. And so I just want to mention, right there in the back, Michelle Hramatka and Kristen Zygmunt. I want to just congratulate you. It was a very, very well done job. I mean, these things are not obviously easy to do. This topic was, well, I'll say a few things in a minute. But they read the paper, they came to the end of the debate. Well, let me paraphrase. They read the paper and they came and said, who wrote this piece of crap? We can do better. That's more or less what they said. And they did. So, well done. Very well done. So, yeah, and so I don't know why they're still here, because they were up till 5 o'clock in the morning, and like I said, they get an A for the class for doing that. So, but good, I'm glad you're here. Okay, so let me say at least 2 minutes about what they did just before we go on. It's kind of cool. And the problem they're looking at actually is a geometry problem, so it feeds into the topic of the lecture today, which is going to be about geometry and data, things that I'm working on right now. Some of you had asked if I could talk more about it, and so that's one of the things I was talking about. So the problem that they were looking at, the problem that people have been looking at, art gallery problem. How many of you heard of the art gallery problem? Art gallery.
Heard the name.
Heard the name. It was immortalized in an episode of Numbers. How many of you seen that TV series Numbers? It ran for many years. The basic plot line was, there's an FBI guy and his brother's a math professor at some unnamed university in Southern California, looks like Caltech, and he sort of solves problems for him using math skills. It's like the best serial I could ever imagine. So yeah, so I watched every episode, and there was one episode in the art gallery theater right early on. I don't know if you remember this one.
Yeah, early one was.
Where he built this kind of model of the museum and actually, yeah. So anyway, the art gallery problem in general is the following problem. I give you some region, but think of it as an art gallery, right? So I have some art gallery, and maybe it's a modern art gallery. So instead of looking like a gallery, it looks like this. That's it's modern art gallery. Something like this. And you have expensive paintings on the walls, and you have little exhibits in the middle of the room. And so you want to guard them. And what you'd like to do is install some kind of camera monitoring system. And these are clever cameras. They can see all around. They're sort of rotating very fast. So they can get a 360-degree view of what they're seeing. But you have to place them in some place so they can see everything. Because you don't want any dead spots. If you have a dead spot, someone can kind of get to the dead spot, maybe use that way to finagle around the room, get something and disappear. So the art gallery problem is how do you place guards in a region like this so that every part of the interior is covered? With the assumption that the guard can see kind of everything around it as far away. So we're going to make some unrealistic assumptions. The guard can see as far as it wants, and blah, blah, blah. And there are ways to change those assumptions. So you might say, okay, well, I'll put one guard, I don't know. So this is going to be an interesting thing. So let me just sort of project this out like this. This is kind of a visibility sight line. So maybe, maybe I'll put a guard somewhere here. Because now you can see all of this. You can see all of this. Actually, you can see all of this. So this one guard here is going to see everything. Kind of got lucky in this example. So it's called a star-shaped polygon. So the answer to this problem is 1. In fact, one guard can guard this polygon. So now I can say, well, suppose that I have a general polygon. So I have a general polygon with n vertices. Right? How many guards do I need? And of course, it could be very jaggedy, it could be very irregular, and there's no easy way it would seem to give an answer to this question. But in fact, you can give an answer. And the answer is something like n over 3. I'm not sure there's a floor or ceiling on it. You guys ever use floor or ceiling? It's a floor. You can always guard any polygon n over 3 vertices. And the actual proof that you can do this is quite easy. Because what you do is you take your polygon, let me draw a new So let me try and get a polygon that actually looks interesting. But this is definitely not star shaped anymore, so that's good. Well, now I just made it star shaped again. I just can't control myself. Okay, it looks like this. Okay? And so what you do is you compute a triangulation, any triangulation of this polygon. What's triangulation? Basically, you connect up the vertices so that you only left this triangle. So you might do this, and you might do this. Let's see. Oh, okay, I'm going to make it very cramped. Okay. Let's see. Yeah, I was going to. Okay, let's do this. Doesn't look a little easier. Okay. You'll have to trust me, these are all triangles. Okay. So now I've divided my polygon into triangles, but what's interesting about this? Well, what's interesting about this is that for every triangle, I only need one guard. Okay? Because the triangle is convex. And if I draw any triangle and I can put a guard anywhere in it, it'll see everything inside it. There's no little bumps or anything. Okay, so what do? I'm going to take 3 colors and color each of the, I'm going to color each of the vertices with one to three colors. Okay, so I just color it. Now, let's see, so do I need to color in that? Yeah, so let's say I color this red, green, blue. So I don't want an edge to have the same color. So red, green, and so on and so forth. I'm missing a little detail here, but I think you can always show that you can color this with 3 colors. Okay, such a polygon can be colored with 3 colors because it's triangulation. Yeah. So once you do that, every triangle now has 3 colors attached to it. Okay. And there are n vertices. So if you look at the number of R's, the number of G's, and the number of B's, right? At least one of them has less than equal to n over 3 vertices in that set. Right? Because if I've colored them all R, G, B, and there are n vertices, one of the 3 classes must be less than n over 3. This is the pigeonhole principle, right? One of the 3 must be less than the average. Right? Okay? Well, we know that every triangle is touched by that R. Take that as your guard. So now you maybe take this guard, that's green, you take this guard, that's green, you take this guard, that's green, and you're done. And so you've proven that you know 3 vertices. So this was proven in the middle 70s, a long, long time ago. And you can also show, it's not what, in fact the example looks somewhat like this picture. It's called a comb. That this is a hard example, that in fact you need n over 3 sometimes. Okay? And so people have spent a lot of time trying to worry about, okay, what happens if for any particular instance, can you come up with the optimal solution? And that's an NP-hard problem. You say, well, can you approximate this? Well, that's also kind of hard to do. You can get a log n approximation. This is kind of like set cover. It's a bit hard to do anything else. There's some special cases where you can. And people have looked at orthogonal polygons. So an orthogonal polygon is a polygon on a grid. So you no longer have these weird angled edges. Your polygon looks like this. Always like this. So maybe this is a contemporary art museum, not a modern art museum. Right? And now you want to guard this. And one might argue this is in fact a more realistic art gallery you might want to guard as well. And so it turns out you can do the same question for an orthogonal polygon, and the answer is slightly different. Because it's orthogonal and you don't have these weird angles, you can do a bit better. You only need something like n over 4 guards to guard this polygon. Okay. And so again, people looked at various sort of variations on this theme. And one interesting variation, and this brings us to the paper that Michelle and Chris were looking at, was if this polygon is kind of divided up into little pieces. So let's imagine this polygon is now divided up into little pieces. So we're extending all these things out. So you have some kind of grid here. Okay? And let's say we'll call this object like a domino, we'll call it a polynomial. So a domino would just be this, right? This is a polynomial, it's got more than a few modules. And you can say now, okay, I have this polynomial, it has m vertices in it. Obviously, I can guard it by putting m squares in it. I can guard it by putting one thing in here. So at least you can do n. Can you do any better? And this is one way of attacking this problem. For example, you can show that for something that looks like this, you can guard it in something like m over 3, m plus 1 over 3 polyominoes, which is actually better than this bound if m is less than, so this number here is less than n over 4 if m is less than something like 3n over 4 or something like that, minus something. So there are cases where you can actually do better than the n over 4 board if you know something more about the polygon. This is a very special kind of polygon. For example, I can't have something that looks like this. I'm not going to have shapes that look like this. And this is part of the problem, right? That this visibility is kind of messed up in here. Whereas here I have this clean, all squares that overlap exactly the same amount, or rectangles overlap the same amount. And so, I guess this brings us to the punchline. So there was this paper a few years ago, and that was part of the report that showed this, in fact, bound. That showed that if you have these polyominoes, you can get this bound, and they showed how to do it. They showed it's NPR documentally. They did a bunch of other things. And what these guys showed is that you can come up with a different algorithm. So they have a new algorithm that basically has a couple of nice properties. First of all, it still always gets n plus 1 over 3, right? And there are many cases you can prove that there's an infinite family of graphs. So let's say a GI, I go to infinity, where the number of guards produced by their algorithm, okay, is less than half the number of guards produced by the other algorithm, polynomials. Which is kind of a nice result, because I say, okay, we have that method, we have this method, and this one is, sometimes for an interesting class of graphs, it's twice as better. You only get half as many guards. The thing that we're still working on that we haven't been able to show, or they haven't been able to show, I've just been cheering them on, is that their algorithm for all inputs is less than or equal to the algorithm produced by the other one. And I think they can do it, but let's see if they're going to do it. So this is actually an interesting new algorithm, and there's many good reasons why it works the way it does and why it actually can improve things the way it does. It uses some nice subtle observations about using the geometry of the space as opposed to using the graph structure of the space and so on and so forth. It's a very nice piece of work. Anyway, so that's what they did for their project. And we submitted this to the geometry conference today morning, 5 o'clock. And that's the story of the paper. So anyway, so let's move on to the rest of the topic of today, and it is again about geometry and about data. So some of you have come to talk to me about my research, and some of you have asked me if they could work with me, and so you've heard some of this before. And so the basic theme of what I do, and I guess I gave one of these research forum things about this as well, is that I look at sort of problems in large data, right? And, forget the large is the problem, just problem in analyzing data. And it turns out that for many of these problems, the way to sort of think about what's going on is to think geometry. What was that? You think of data as basically a collection of points in some very, very high dimensional space, and there are patterns in that space. And to understand what those patterns are, semantically what they mean, you have to understand the geometry of that space, right? And so, for example, a simple example of this is something like clustering, right? I want to cluster data, so I want to group it into pieces. What you typically do is you take the data points, you put them in some high dimensional space, so you have feature vectors for each point, and you have a bunch of numbers in them. And now you look at them in the space and you run some clustering algorithm, and maybe a clustering algorithm produces things like this. And you say, aha, these points are now similar to each other, and these points are now similar to each other. And I can analyze them, try to find representatives of them, and do all kinds of things. And if you want to hear more about this, you can come to my class next semester. But this is again an example of going from sort of you have data plus meaning. And I'm being a little dangerous here, and essentially claim that I can extract this from structure and geometry. And this doesn't always work. There's meaning that goes beyond what you can speak about geometry. But it's a very powerful tool. And again, clustering is one example, classification is another example. You're doing nearest neighbors, different than the classification method. There's a whole bunch of things where this idea works. And so therefore, in order to understand a large class of different questions, it helps to understand the underlying geometry. It helps both semantically and it helps from an efficiency perspective. From an algorithm's perspective, which is the kind of thing I know how to do, how do you make these things work fast, especially in regulations? So the key parameters in all of this are n and d. You have n objects and you have d dimensions. And the very first thing you might want to ask when you do geometry is, okay, if I give you a bunch of points, like what does the shape of these points look like? Right? What kind of shape do they have? And so you might say, okay, I have these points, and maybe they're even in 2 dimensions right now. It's a very simple point set, and I want to describe their shape. And so I might say, oh, okay, well, one way to describe the shape is to look at the boundary. So I kind of connect up the boundary. You can think of this thing, I take a gigantic rubber band, and these points are nails on a board. You just let the rubber band go and see where it stops. So you get something like this. And this object is so useful that it's got its own name. It's called the convex hull. The convex hull is kind of like the sorted order for geometry. It has very strong connections to sorting, much more so than I just said. But it's something it's like a basic tool. When someone asks you, well, what's the application of sorting? You're going to say, well, it's just everywhere. You know, there's no specific killer application of sorting. You just use it all the time to process your data. Similarly, convex hull is something you may not have a killer application for, except you want to find shape, but you use it all the time to understand your data, to sort of pre-process it. For example, if you just want to look at the body of your data, you can throw everything away that's inside. Right? That's all you just say. And they're very nice. So people study algorithms. How do you compute the convex hull of a set of points? And in fact, there are dividing Poincare algorithms. There are algorithms. Greedy algorithms don't work very well, but if you randomize the order of your points, you can do them. So the randomized algorithms. There are all kinds of nice methods to sort to compute convex hulls. And in 2 dimensions, it takes something like n log n. Okay. And this seems like a reasonable thing. The size would be n. So this is 2D. You can do the same thing in 3D, of course. Ask the same question. You have a convex hull, which is more like a, and you can say, what's a convex hull? So you might have a bunch of points, and you want to find some kind of boundary that captures them. Right? And this again takes n log n time. This is not obvious why it should. It's not even clear that the output size is reasonable. Output size could be complicated, but actually it's linear. And this takes a bit of thought, but you can prove it. Basically because the boundary of a sphere is kind of flat, morally speaking. So you're not going to have, by Euler's theorem, you're not going to have more than n. And so you can do this in n log n time. So these are some of the questions you look at. How do you compute the convex hull? It's a very basic question. And as you go to higher dimensions, things get a bit hairier. In general, the runtime bound you need is something like, don't quote me on this, but something like n to the, let's see, and there's some log factor. Which is quite bad if you think about n is like 1 million and d is like 100,000. It's not a number you want to be working with very much. Not that I'm saying, 100,000 squared, 1 million squared is any good, but 1 million to the 100,000 is definitely not good. So just like the convex hull, there are other objects you can construct out of your data that might give you some sense of what it looks like. And again, what it turns out happening, and where this thing starts getting interesting, is that all of these numbers you get have this something like n to the d kind of behavior. That if you go to d dimensions and you want to compute some object, either the time to compute it will be n to the d, or the object you get when you finish computing it will be a size n to the d. And this is what is known as the curse of dimensionality. So I'm jumping over basically 30 years of development in geometry just to get to the curse of dimensionality, because this is something that I think is very interesting right now. There's a lot of stuff there that is interesting in 2 and 3 dimensions that is worth studying, but I'm not going to talk about that in this lecture. So this curse of dimensionality was always an issue, but it's become even more of an issue because I actually have data sitting in 100,000 dimensions. It's not some theoretical concern. I actually have this data and I actually want to do something with it. And any interesting problem I want to solve bumps up against this problem, which basically means it's hopeless. I can't do it. Right? We're not talking about NP hardness per se, although some of these problems aren't NP hard. We're talking about just a basic inability to attack these questions in high dimensions. Right? Even if D is a constant, it does not console us very much. So what do you do? Right? So there are 2 problems here. Right? There's what I'll call the N problem. and there's the D problem. Right? Both these numbers are bad. The base here is bad, and the expletive here is bad. So there has to be something we can do about this, otherwise we're basically foolish. There's no way we can actually analyze data. And so it turns out that over the last, I don't know, let's say almost 15, 20 years almost, 15 years at least, what we've seen is the development of essentially a new way of thinking about geometry that is both approximate, not surprising, and randomized for the most part. That allows us to deal with questions where if you wanted to solve it exactly, you would be this kind of place. So I mentioned this when I was doing approximation algorithms, right? That approximations are a good thing. It helps you solve problems a bit easier if you're willing to tolerate a bit of error. I mentioned randomization as a good thing. That if you're willing to tolerate a probability of error in the outcome, you can actually do a lot better. And when you put them together, and I mentioned that as well, you can do even more things. And here, especially in dealing with data, is where you have to have both these tools. And so I want to give you two examples of how this works, and both in terms of removing n and removing d, and then I'll mention sort of other directions that people have looked at. So these two results are kind of counterintuitive in their own way, but they're both very interesting. So let's look at the first one, right? The n problem. The n problem is that I have a lot of points, and I want to compute some property of these points, but I don't want to waste a lot of time looking at all this, or I don't want to waste time crossing all these points, because it's just there's too much. And again, you've seen this before. You've heard about things like randomization and sampling, and something. Then you think like okay, there might be some interesting way in which I can deal with this issue. And so it turns out that there's a very beautiful idea in geometry. It's called a coarset, and it works something like this. Suppose I have some problem, and I can express the problem as some kind of function that I want to compute in the data. And let's say that function is numerical, some number I want to compute. So for example, I might want to say, you know, what is the best clustering into groups into k groups? And in best terms, I measure the cost of the clustering, it's some number. Or I might say, what is the radius of the ball that encloses all these points? Again, some number. So there's some number associated with my data. Okay. So if I have a data, let's say this number is f of t. And what I want is some set, we'll call it S, which is maybe a subset of P, and maybe not. But for now, let's pretend it's a subset. With the property that, and we'll fix some parameter epsilon, fix. Okay, some small epsilon greater than 0. And what you want is a property that, let's say again that you're trying to optimize, you're trying to minimize something, right? Or even maximize something. So you want the property that f of s is very, very close to f of. And when I say very, very close, it might mean, okay, it's within some 1 plus epsilon factor, within some 1 minus epsilon factor, or something very close. It's 99% of the value f of p, or it's 101% of it, or so on. Again, the exact definition depends on the problem. And, well, this is easy, right? Just take p itself. The point is that you want s to be very, very small. And if you can find such an S that does this for you, then S a coarset. It's a set that kind of captures the core of what you want the data for this particular problem. Now, a coarset is not likely to be universal, right? A coarset that works on one problem may not work for a different problem. That's okay. We're going to define it with respect to a problem. It'll turn out that there are corsets that work for a large class of questions. That's nice too. But usually a coarset is defined with respect to a particular problem. And you want this thing to be really small, right? I mean, ideally, you'd like it to be, square root, logarithmic, something like that. So let me give you an example of a coarset, which is shockingly good. So shocking that it was one of the first ones producing, sort of opened up people's ideas to the fact that corsets could be quite awesome. So let me define a problem. We'll call it the enemy, not the building. Yeah.
That f is a function
of the points.
It's some property of.
Yeah, I'm going to give an example of f now. So the example of f is going to be the minimum closing ball, which basically means that I have a bunch of points. And again, you should Train yourself to think these things in 100 dimensions, not 2, because that's how we always do. Actually, okay. And I want some ball. Well, let's make it a little bit more complicated. Some ball that encloses this, right? So I might say, try to put it here, and right. It has some radius. So some ball at some center of radius r, such that E is a subset of and R okay. Does this question make sense? So I give you a bunch of points, I want to find a ball like this. And again, you could think of this as kind of a bounding volume, kind of a shape estimator. It turns out that in an appropriately defined dual space, this boils into doing unit classification. And I won't get into that, because this relates very strongly to unit classification into class and lines. And the question is, how do I solve this? So it's not, so if the point you want has to be part of the A-code, then it's kind of easy. Just take each point one by one and try them out. But it's not hard to just see that that's not going to give you the optimal solution. Taking one of the input points and treating that as your center is not going to work. And one example of that would be something like this. The optimal ball would be something you would place right here, right? If it's an equilateral triangle. But if you took any of the input points and tried to make a ball around it, that would be a lot bigger, because this distance is much more than this distance. Right? In fact, that would make it even bigger than that. So you don't want it to be the input points. You're not going to get a good answer. You can prove that this is an approximate answer, so that's one thing. But if you didn't want the exact answer, you have to find some point somewhere in the space in the middle, which makes now the search a little bit harder. How am I going to find this point in the middle? And so it turns out that if you squint at it long enough, it starts looking like a linear program. It's not quite a linear program, but it has enough of the properties of a linear program that it, it's kind of like it's not fully a duck, but it's kind of like a duck. So you can treat it like a duck, and it'll give you a solution by linear programming, but that's very expensive. It'll be into the DU and so on and so forth. So you want to you want to do this better, and what you'd like to do is come up with a small set that has this problem. Yeah.
Why can't we choose the center? Just take the center of all.
What is the center?
The center is the center of the circle. I mean, the average of all the coordinates of the point.
The average of all the coordinates of the points. Well, that's a good idea. Let's just take the centroid of all the points, and that will have to be your minimum solution or close to minimum. Is there any thoughts on what might go wrong?
Well, if you have a lot of points, don't we want to find a solution that involves less points?
Right. But ultimately, my goal is to find the ball.
I thought of a different thing.
Wait.
So say I had a graph and I had 1 million points far to the right and 1 point to the left. Well, I guess that.
Yeah, go on. Good. Go on. So the average would be.
Yeah, it's going to be right in the middle of on the far end.
So what's going to happen?
So
what's going to happen to your ball? You're going to lose a factor 2 almost. Right? Because you would want them with the midpoint to reduce the radius, but now you've pulled all the way up to one end because the average, now you're going to be double the cost. So it's not a bad heuristic, but it will not be the optimal solution. Yeah. Yes?
What if you tried to find the convex hull?
Find the convex hull, and then what do you do?
And then just take the average of those points.
Another good. So instead of taking the points themselves, the points are going to mess with the proof. You take the convex hull and then average of the convex hull.
It will be equal almost close to the average.
Will it?
Yeah.
Why? In that example, it won't, because all those points that are in a big mess, they'll go away in the convex hull. They won't be part of the convex hull.
If there's 1 point far, then you make because of that 1 point. Now you're actually weighting the point more to the right.
Yes, but you do want a ball that covers the point.
But the convex hull is just in one dimension, right? So
No.
It's not.
Think of a high-dimensional rubber sheet and let it go around your points. It wraps The convex hull formally is the smallest convex set that contains all your points. And you can show that in fact the set will be a polyhedron. Remember polyhedron? LPs? It's a polyhedron. So you can actually write out the problem of convex hull as sort of solving some in your program. Which of course gets us to the real point where you can't use convex hull. You're not really making the problem any easier. To compute the convex hull itself doesn't take as much time as it's going to compute the center itself. So you haven't actually made your life any simpler. Because here's what you'd really like to do with this set. Right? Suppose you have some very expensive algorithm, convex hull or whatever, that you don't want to run the data. But suppose I could compute this set that has this property and this property. I could take my expensive algorithm and run it on this instead. Because if the set is small enough, my expensive algorithm on smaller data won't be so expensive. Right? If I take an algorithm run in square time, and I run it on a set of size log n, then I'm spending log squared n, not n squared. So in general, what you're trying to do with the core set, right? So I should add some more things. So I have my function f of p. And let's say it took time g of n to compute f. And let's say I can compute the set S. So S is much less than P, and f of S is roughly equal to f of P. Then to compute an approximation to f of P, I basically have step 1, compute S, step 2, run G on S. And so this first step usually is very simple. Let's say it's linear. But then instead of paying G of n, I'm paying n plus G of S, which hopefully is a big win if S is very small. So that's the reason I want to do this. I want my core set to act as a proxy for my set. So that if I do want to compute it, I can compute on this instead. This is a lot cheaper. Or I can take this around as the object I want. So I can throw away all my points and just keep this, because it's a good representation. So let's get back to the MEP, right? So if you think about the MEP, how many points do you really need to describe that ball? I have n points, but how many do I really need?
Two.
Well, think of this in 2 dimensions.
3.
Is 2 points enough to define a ball?
3. We have the center and the radius.
That's not. How many points are we aiming to it? I've identified the core set. So 3. In 2 dimensions, 3 points will define a ball. Right? If I have 3 points, I can always fit, unless I have a straight line, I can always fit a circle through this. I'm not even going to try.
Unless they're collinear.
Unless I collinear, which I said, unless I ignore like this. So there really are only 3 points that govern any circle, or in general, you do d+1 points for any ball. So why, I should be able to find the set S of size d+1. It must exist, because once I finally find my ball, it's going to touch these d+1 points. It turns out that if you want a ball that is minimum, you need an extra feature, you need an extra point to make sure that this works. And in fact, you can see the following. Let's take any ball that claims to be the optimal solution, or close to the optimal solution. Okay? So let's say this ball claims to contain all the points. Okay? Then I claim that you can't have a situation like this. So I'm going to draw a half plane. Imagine a hyperplane going to the middle, rubber hyperplanes from the middle. I can't have a situation where all my points are on one side of it. This ball cannot be optimal if this is what the picture looks like. And the intuition is something like this, right? If all the points are inside one side of the hyperplane, I should be able to shrink it. This can't be optimal. Something has to hold that ball out to make it optimal. There has to be some point on the other side, somewhere here, to pull that ball out. And this is true for every hyperplane. So we have some way of describing what property an optimal solution must have. It must have this property to take any hyperplane and slice that ball in half. It's going to have stuff on either side of it. It can't be anything else. which basically means you want points that are kind of far away from each other. You don't want points that are close. If you want to find this core set, you want to find points that are kind of on the outside of this point set. Because they'll be the ones who will represent the points that better, the point you're finding for. Okay. So here's the algorithm. Any of you are familiar with clustering, you may have seen this before. So take a point, take its furthest neighbor. I have 2 points. Take its furthest neighbor of the two again. So the one that's closest distance inside them is as large as possible. I have 3. Keep doing this. At some point I'll have k points. I'll stop at k steps. That's my core set. And the key thing here is that if you want an epsilon error, you want your core set. So suppose I want a property that the MEB of my core set, right? Now this is a subset of my input. So the minimum enclosing ball of this input will always be less than the minimum enclosing ball of the original point set, right? So it's always going to be less than it, but I don't want to be too much less. I want to be close. So I want to say something like, this is greater than or equal to 1 minus epsilon times MEB of the P. Right? So hopefully now you're used to seeing approximations. You know that this means that if you think of epsilon as, let's say, 0.1, I'm saying that the radius of the enclosing ball for S should be 0.9 times the radius of the enclosing ball for P. And if I make it 1.01, I want it to be 0.99 times that. So very, very close to the actual solution.
Why don't I want it to be true?
Because life is not that simple. I'm not that lucky. I can prove, I can show you that, to make it equal, that I just solve the problem. I mean, I would have found those to some point that that's equivalent to actually solving the problem here. So I'm not hopeful that I'll get an exact answer. I want to get the approximation. But here's the thing. Let me tell you how many points you need to get this. How much does k need to be? It turns out that k, in this particular algorithm, there's a slightly better one, but in this particular algorithm, k is something like,
So when you say furthest neighbor, when I have 2 points, the third point will be farthest from both of them?
so what you mean is that you look at the 2 points, and you look at this new point. You measure its distance to the 2 of them, and take the smaller one. And you want that to be as large as possible.
Okay.
So, what this is saying is that if you pick 1 over epsilon squared points, and take their minimum enclosing ball, it will be within 1 minus epsilon of the true minimum enclosing ball. And I want you to think of it for a minute about how shocking this problem is. Or it does not depend on n at all. This is not square root n or log n or whatever. It does not depend on n. And even worse or better, it does not depend on d. It does not depend on the dimensionality of the space. You could be in 2 dimensions or 100 dimensions or 1,000 dimensions. I don't care. This bounce will work. So this is what is both bizarre and cool about this object, that such an object actually exists. That you can find a core set of size independent of any interesting parameter of the input. All the sizes of the input, I don't care. All I care about is the error. If I want an error of 10%, I want 100 points. I don't care what they take. This is a very strong result. This is what we call a core set. And this is the ideal world for a core set. So things only go downhill from here. But if you can get this, you're very happy. And so you can see why such a result would be very useful from the perspective of data analysis. Because it's telling you, at least there's some hope, that you can actually reduce the data size down to a constant and still retain the ability to compute properties of interest, which in this case is the minimum enclosing ball. And course, you might say, oh, who cares what was involved? And you'd be right. Maybe not, we all would care. But the point is that we can build this framework. I can take a problem I do care about, like clustering. I can say, okay, I want to compute a clustering of data. I want to compute a k-median clustering. Is there a small set that I can run my algorithm on that will give you the same answer? And in fact, there are. So you can ask all these questions now because you've sort of opened the door with this possibility.
But at the end of the day, you're only doing the convex, the function you're assuming is in some sense changing equally in the constant, in the convex.
That's only for the MAP. If my function was not based on the boundary, then that's not true. If I'm doing clustering, then the function is looking inside the data set as well.
But if I have a function which is, let's say, ring-based kind of function.
You can still do it. Min with annulus, for example. Suppose your function is, I want to find how spherical the data is. So you want to find a minimum width annulus that encloses the data. So in other words, you want to see if there are two rings. So you want to see, this is my data. It kind of looks spherical, but I'm not sure. And I want to see if there's, that encloses my data. Right? And I want to minimize this quantity here, make it as narrow as possible.
Oh,
This is called the min with annulus problem. And you can actually get a course into this one.
So I define MEP in such a way that I get rings.
No, it's a new problem.
It's a new problem.
You come with a new course set.
Okay.
But there's a nice, here's a cool trick, right? For this particular problem, if you draw a paraboloid, which is one dimension higher parabola kind of thing, and you take all the points and lift them up, then your annulus basically becomes the points are between two half planes.
Okay.
So now you're asking, okay, can I find a course set so that I can sandwich my points between two flat things? And then if you do some magic with that, that becomes a ball again. So they're all connected. But you have to use the right theorems. So the thing is, the minute you can ask these questions, you can start looking for these connections. And there's a whole class of questions now where they're all, okay, if I solve this, I can solve this, and I can solve this, and I can solve this. So we have a good collection of tools in our toolkit to do courses and of various kinds. There are some courses that are not so strong that they depend on the dimension but not on the point set. So in general, right, I might be able to get something like if I got a course set, maybe a course set that's not so great would be something like 1 over epsilon with d, which is not good at all. But it's much better than n with d. So I replace n by 1 over epsilon in all my expressions, which for some problems can be okay. Okay. Yes.
So it's nice that we could duplicate points, but how do you find the first neighbor from each k?
How do you do it?
What's going to be in square count?
Actually, yes and no. If you don't know anything about your points, then yes, if you try them all one by one, it will take n squared, and that would be terrible. But you can actually do a lot better than that. So here's an algorithm. So you can actually run this algorithm the following way. So let's imagine data is coming in one by one. Okay. So you take the first point. When the second point comes in, let's say I'm the first point and the second point, I'm going to move a little bit towards you along this line joining us by some carefully chosen amount. Okay. Now the third point will come in. I'm here. And now I'm going to move a little bit towards Nitin right there in a carefully chosen amount. And the next point comes, I do it again. You can show that this different algorithm, not this one, will get you the same answer. So you pick all these points along. So you do something and you move a little bit, you do something and you move a little bit, you pick all these points. And so you're absolutely right, this is inefficient, but there are much more efficient algorithms. So in some sense, this was just a proof of concept that such a set does exist. And now we can roll up our sleeves and say, okay, let's make it possible. And that's often how these things happen. Someone comes with a horrible algorithm that solves a problem, and then people just whittle it down to become very efficient. So yes, so you would not want to implement them this way, but there are better ones. Some of them, for example, involve random sampling. That's not for this problem. For some problems, you say, pick a random sample, it's going to be good enough. And you can prove it's going to be good enough. And so that's also easy to do. So there's a whole industry of work here on how to reduce data size and still retain essential characteristics of the data, depending on the problem you're working with. So each problem gives a different lens in the data. For example, I have a matrix. I want to retain some low-rank approximation matrix. There's techniques for doing that. Let's see, what other kinds of questions we might have?
So if we take, so in big data kind of, they take large amounts of data, which is in some sense number of points and dimensions, but they do it based on eigenvectors and stuff. Are these related, or in some sense they would be completely different?
They're related sort of morally speaking, that they're trying to get the same goal.
Yeah,
the techniques are often very different. Things based on eigenvalues are looking at different structures of data.
So in some sense, would I be losing some data in low eigenvalues, or would I be losing data from high eigenvalues also if I do this?
That's a very good question. If you compute the MEP, you would lose a lot of the eigenstructure. Here's why. The eigenstructure of data, and again, maybe I'm going ahead, people are not familiar with this, but roughly speaking, if you have a bunch of points, let's think about PCA, which is one simple example of this kind of thing, right? So I have a bunch of points, and let's say my points look like this, for whatever reason. If I were to compute an associated matrix with this data, look at its eigenvectors, what you'd expect to get is an eigenvector with a big eigenvalue along this direction, and an eigenvector with a smaller eigenvalue along this direction, because it's identifying the principal components of the data. If I start removing data to find this ball, I've destroyed the structure entirely. Because the density is what matters for things like this. Finding that in an enclosing ball, I'll get, this. Which at the very least is going, does my data look like this? Does it look like this? How much is the strength of connection distance? All go. So this particular problem, it will destroy our eigenstructure. But that's the point, right? My F can be different. The way to think about these problems, and that's what I'm talking about here, is think about the F and then think about how you want to approximate. For different Fs, you'll have different ways of doing the approximation. What I'm showing you is that there is hope. There's at least some hope that you might be able to do something. It may not look like the algorithm I gave you, but there's some idea. And so there's a whole framework to think about these questions, and there's tools you can use. Okay? Any questions? Okay. So this is so much for the large n side of things, that you want to reduce n. But D is, in some ways, as or maybe even more important, because it goes with the exponent. And it would be really nice if we did have to work with high dimensional data. We just work with low dimensional data. If everything was in 2 dimensions, it would be so good. I'll ask you what happened. So the question that you can ask is, so if you go to what's called the problem of dimensionality reduction, is, can I go from data living in a high dimensional space, right, to data living in a low dimensional space? While preserving, again, some essential properties of the data. And this is also a big win, right? If I go from D to D minus 1, I've speeded up my bad algorithm by a factor of n. Because I've gone into the D to n to D minus 1. If I reduce D by half, I've basically made my right hand the square root of its right hand. So small changes in D can make a big difference to your algorithm. So the general area of dimensional reduction is how to do things like this. And this has not just algorithmic value, but it has semantic value. And what I mean by that is that if you have some data and you're constructing a feature vector to represent your data, maybe not all those features are important. Maybe some features are junk. Maybe they're just causing you a lot of trouble. You'd like to get rid of them. And things like PCA, for example, are ways to identify the key important features of the data and throw away the rest, which is exactly dimensional. So people are doing this for a long time. Identify the key features of the data. If you have maybe 100 features, I want only 10 of them. That's a dimensional reduction, 100 up to 10. And before people did it because there's meaning in those 10. Now it's also interesting because we know that computationally it's horrible to use 100. It's not so much, it's much better to use 10. So now we have an algorithmic question. All right. So there is another canonical result with the same kind of shock value for dimensional reduction as there is for reducing. So I want to tell you what's the result, and I won't prove the result for you. There are probably 100 proofs of it, but I'll just try to give you a sense of what it's saying. So the following statement can be shown. So suppose I give you n points, so I give you points p1 up to pn in some high dimensional space. Okay, so it's RD, which means each point is d coordinates, right? Each value can be a real value. And let's just say that all these points are in a Euclidean space, which in particular means that the distance from one point to another is equal to the Euclidean distance. So in other words, you do this, you take the sum of the square roots, you take the sum of the squares of the distances, take the square root. But there are many ways to measure distance between points in a high-dimensional space. This is actually one of the most common. So it's called a Euclidean space. It's Rn, Rd with Euclidean norm. So the statement is the following. There exists a mapping from Rd to Rk, and I'll tell you what k is in a minute, such that the distance between points, let me see if I can so in other words, if I take my input points and they have all these distances between them, which in some sense captures the structure of those points, all the distances between them, I can put them into a space, Rk, such that all the distances are still roughly the same. And there's usually a sort of normalizing factor because there's not enough room usually to map things out. But you use some kind of scale factor here. So we'll ignore that for now. So does the statement make sense? The question, the claim that we're making, that I can take points and project them down into a lower dimensional space, so that all my distances, the thing that I care about, are roughly preserved.
When you say the distances you care about, the ones you care about are you p are they p I minus pj or f of pi minus f of pj?
Both, right? So pi minus pj is the distance in the original space.
Okay.
F of pi minus f of pj is the norm is the distance in the target space, which is also Euclidean. So I want to say that the distances in the target space are more or less like the distances in the source space. And again, the reason the same as before. If this is true, then any algorithm that involves using distances is going to behave the same way in the target space as it is in the source space. For example, I want to do clustering. Instead of running clustering in my source space, which could be expensive, I project it down to a much lower dimensional space and run clustering there. Because my distances are roughly the same, I expect roughly the same answer. And that's the idea. Okay? And it turns out you can show that k is roughly again, the shocking thing here is that k does not depend on d. I don't care if my points are in a 100,000 dimensional space or a 1 million dimensional space or an infinite dimensional space. All that matters is how many points I have and the error. And there's a very shocking way of saying this as well. So here's another way of asking the same question. It turns out to be equivalent to this. Suppose I give you a bunch of vectors, okay? And I want to make sure in d dimensions, and I want to make sure they're all perpendicular to each other. How many vectors are you going to get? So in 2 dimensions, I want you to give me vectors that are all perpendicular to each other. Right. So there. In 3 dimensions?
3.
And so you do d. What this result is saying is that if you're willing to tolerate vectors that are not orthogonal but slightly less than orthogonal. So in other words, If two vectors are orthogonal, we know that u v is equal to 0. The inner product is 0, right? By definition. Suppose we allow, this. So now we know you can have, in d dimensions, you can have d vectors here. Here, you can have 2 to the d. If I allow my vectors to be not orthogonal but just slightly off, I can pack exponentially many vectors in that space. It turns out to be an equivalent way of saying what I just said before, that if you want to preserve distances, you only need something like log n dimensions, where n is the number of points. And that the n points between them, they don't have that much information. I only need log n dimensions to capture that information. So this result is called the Johnson-Winterstrass lemma. So this is after the two people who invented it, who proved it, discovered it, Reinhold Platoni and New And you might ask, well, what is this magic function f? Like, how do we do this? It turns out to be stunningly easy. The easiest way to think about this is, I do the following. So I have a point. I want to go from R to the D to R to the K. So I'm going to build a matrix, which takes a point, which has D coordinates in it. So this has D rows in it, and it has K things. Just do the right job. And each entry is chosen uniformly at random from the normal distribution. That's it. It has nothing to do with the data. It doesn't even care what the data looks like. I can write this matrix out right now that will work for all your data. Just pick every entry randomly from a normal distribution. It will guarantee this. And if you don't,
Normal is uniform?
normal distribution, Gaussian. N01, so mean 0, variance 1 Gaussian. Now, if you work with matrices a lot, you will realize one thing that's not quite nice about this. This matrix is very dense. You can do a little bit better. You can say, well, okay, I don't like N01s. I can say, choose from the following distribution. Let's see. Your distribution is 0 with probability 1, probably 2/3, plus 1 with probability 1/6, minus 1 with probability 1/6. So every entry is either 0, plus 1, or minus 1 with these probabilities. It still works. You can still do this dimensional distribution and everything's cool. You can even reduce the dimensionality even more, but that gets into more fancy. The number of coordinates and this number of non-zero entries is even more, but I won't get into that right now. And so this result has been proved, probably 20, 30 different times in 20 different ways. You can think of this, and Jeff Phillips has notes on this, as a kind of a generalization of a Chernow form. We talked about Chernow forms in the randomized algorithm section. You can prove this using that idea. It's basically a Chernow form. It has, you can think of this as an information theoretical inequality. You can think of it as many different things. But this fact, right, this basic fact, to tell you something about the geometry of the space, saying that in a Euclidean space, I never need more than log n dimensions, log n order dimensions, to capture what I want. And that doesn't be very useful, both practically in terms of just doing the embedding, but in terms of intuition about how these things matter. And if p is more than log n, I don't have to worry about it. So normally you think, oh, if we have n, we have d, and d is very big, it doesn't mean. Yes?
Can you give geometric intuition of how this works? Like how? Yeah.
The intuition is what I just said. That if you want vectors that are orthogonal to each other, there's only d vectors you can fit in a space. But because of the weirdness of high dimensional space, the minute you allow yourself to be a little bit less than orthogonal, there's suddenly a lot more room there. You can pack a lot more things in because of that extra little wiggle room there. Now, if you want intuition for why that's true, that's a bit hard. But that's what's going on. And the way to think about this is that the distance between 2 points so let's say these points are all the norm 1. So let's say x equal to y equal to 1. By scaling, this doesn't affect us. So we're saying that x minus y whole squared is equal to 2 minus 2 xy. And that's kind of weird. That's what these are. I'm not saying that this is a proof. I'm just saying the intuition comes from it. That everything matters, the inner part is what matters.
If I keep the matrix, can I get back the data with a different error?
What does that mean?
Like if I have the RD to RK matrix mapping,
Yeah.
and I want to do RK to RD.
No, because it's lifting now. You're projecting into a random subspace. You've destroyed all the information about your data, except the distances between them. So you've really scrambled it like crazy.
Okay. But if I keep the matrix, even then I can.
You can't go backwards because you're projecting down.
Can't do it.
So there's a whole bunch of points all going to end up in the same spot. Saying once you're there, it's a lossy mapping. But the claim is that it's not lossy for the thing you care about. The one thing you care about, the distances, is not lossy. But it's lossy for a bunch of other things. And how many of you have heard of kernels and kernel methods? Not in group theory, but in machine learning? Yeah. So kernel methods, you use this a lot as well. Because in some sense, a kernel gives you a mapping from your data to an infinite dimensional Euclidean space. I could barely handle D. What are you going to do with infinite dimension? That's even harder. My algorithm just would not run at all. So it turns out that because of results like this, if you have n points in an infinite dimensional space, remember this bound is independent of D. It's effectively the same as just saying you have n points in a log dimensional space. The infinity doesn't matter. So you get the same structural properties of the kernel that you want. And again, this is something you learn in machine learning next semester. But you have this low dimensional space. So there's two ideas, right? Of course, so you can do dimensional reduction with Euclidean spaces. You can do dimensional reduction on a surface. You can do dimensional reduction on spheres. You can do all kinds of things now. Whatever your data space is, you can ask the question: can I reduce dimensionally and can I prove it? And because of results like this, you can say these things. This result gets used in compressed sensing, for example. If you've heard of compressed sensing, it's this idea that you can take very few measurements, carefully chosen measurements from your scene, and reconstruct the scene if the scene is not got a dense signal to it. And you use properties exactly like this, what's called a restricted isometry property, in order to do it. So this result, this is a paper that was proved in 1984 in a functional analysis journal, has become like the go-to result for a lot of the work in data analysis. It's kind of funny about this. And related to this has been a lot of other questions about, okay, I have one space where I can solve the problem easily, like a low dimension space. Maybe it's a different kind of space. I have one space where I can't solve the problem easily. Can I map my data here to here so I can then solve it here and get some answer back here? So there's a general theory, what I call metric embedding. So I have some metric space with a distance that's hard to work with, like say a graph. But I have a metric space that's easy to work with, like say a tree. Can I map a graph to a tree? You can do results like that. So there's a whole, again, family of results about how you can map one space to another space and so on. This gets into a lot of functional analysis, and if it's kind of thing where you have to know a lot of basic functional analysis, how to think about functions as points and so on and so forth. It gets quite interesting. And so these are some of the things that, in many forms that I look at when I do my research. In fact, another paper that I wrote just today morning at 5 o'clock was basically about how to do dimensional reduction for distributions, probability distributions. So you have probability distributions and you have distance between them. These are not Euclidean, but they're Euclidean-like if you look at them carefully enough, and then can you do something with that? And it turns out you can. You can embed them into a much lower dimensional space and retain the probability distribution structure. So a lot of what we do in geometry nowadays, especially high-dimensional geometry, is about this interaction of geometry, data, high dimensions, data reduction, and questions like this. All the tools you've learned, especially approximations and randomization, get used out here, and many, many other tools, a lot of other mathematics that you have not learned in any one day. And so that's kind of a summary of what it means to computational geometry today. Again, 20 years ago, I would have been a different story. 20 years ago, I didn't even know what computational geometry was. That's the stories. But that's kind of one of the things that is very interesting right now. again, at least in this department, you take any class with Jeff or Vivek or myself, you will keep bumping up against 60, because that's what we do and that's what we like. All right, questions? So some of you came late. I just want to remind you that we will not have a lecture this Thursday and next Thursday. So next lecture, Tuesday is the last one. I haven't decided what I'm going to talk about. I've had some requests from people, so I'm pondering the requests and deciding what I'm going to do. I don't want to say anything right now because I want to promise. It will be a surprise. Yes?
So earlier in the semester, you said that we would have our final projects due during finals, and then at one point you said at the same.
So I think I fixed a date for it. I announced it, December 12th or something. Was the date I announced?
That's 15th.
15th. Is it 15th or 12th?
15th.
Then that's the date. 15th.
So we can. So our homeworks are due at the end of
Classes. Yeah.
and then the 15th for the project. Okay.
Yeah.
Oh yeah, and there will be more questions related. So somewhere in here, in the way the assignments were written, it is said that if we don't do 75% of
Yeah, I confused it.
Yeah.
So the idea is this. And and the first couple of assignments are a bit messy, but after a while I normalized, so all problems is the same score, right?
Yeah.
And so the idea is that for any particular problem, you don't have to get it perfect to get the score. You have to get it almost perfect. For any particular problem.
Okay, but what does it mean? If it has 3 bits, which is 6 points, 6 points, 6 points, and I do 1/6, would I get the 6? If I do 1/6 right, would I get
1/6? Or 1 of the 6 of the
like 3 bits are 6 points, 6 points, or 6 points. Right?
yeah.
I do the 6 points good, but I leave the rest 12 points.
If you leave it completely, then you won't get any score for it. But if you do it sort of partially, you get. If you do it partially, then your score goes to 100 faster than your partial goes to 4.
My question is, would I get 6 points in the first place?
Yes.
Okay, but if I do a little bit here and there and try to get more than 75%, then I get it.
Yes.
Okay, that.
Yeah. The granularity of the 100% is not the assignment level; it's at the problem level.
Problem level, and it's not.
Yeah.
It doesn't penalize me. It gives me.
Yes.
Okay.
The goal is not to punish you for punishing us. And the goal is to make sure you're not like we don't want to nitpick over every single detail. That was what the feedback part was for. The hope is that right now you figured out what to do. Okay.